Hey guys, it's Mr. Fourth Dimension, and welcome to another episode of the Geo Project. So it's well, as of last time, we had some segment stuff basically working, and I've done a tiny bit of work on the code. Not really anything interesting. I just cleaned up a bunch of comments and debug stuff that was left in, and this macro here, the not macro preprocessor stuff that goes from this end if all the way up to this if I moved it. It used to only be inside of this function. And it's up here now saying that this whole thing is the first version of segment collision. So along the way I've suggested that there might be other ways of doing segment collision that we might also want to try, and then we're going to compare them against this method. So we're going to we're going to preprocessor that out, I guess. I'm going to take that all out. And the project's going to stop building, of course, for a little while, but we'll get that fixed shortly. So the new version will have pretty much the same struct, but I even put the struct in there because the struct will be different in that it'll support this S as well. And then, let's see, anything else we need to do to make this work? Cast result, we need this function, of course. So we'll have a copy of this function still available. And that'll be let me check up here. Yeah, okay. Just making sure I understood. Geocast result. And then these are points, so that's geopoint2d. Okay. Geopoint2d. Come on, there we go. 4 times. And that's going to be P1, a P2, a Q1, and a Q2. The question again is, do these collide, or do these two segments intersect? And if so, at what point along the distance from P1 to P2, but also now, along what point along the distance from Q1 to Q2? So the difference here is that we're going to get a 0 to a 1 here and a 0 to a 1 here during a hit. The other one only computed this amount for one of the segments. And maybe we can find a way to do the S in this one as well. But doing it in this new mode is pretty much natural. Now this is a problem I haven't solved for a while, so bear with me, I might get it wrong. What the idea is that we're going to find two equations that describe the line from P1 to P2 and then the line from Q1 to Q2 in the whole space, not the segments, the whole lines. And we find the collision between those two lines, the intersecting point. We solve for that point, and the way we form the lines equations will be so that the solutions, so it's a system of equations, right? And so there are two variables to solve for. Basically, the variables we're solving for are t and s. So we're going to make two lines such that the variables on both of them are t and s, and then we're going to ask where, for what value of t and what value of s do these two segments collide. Now it sounds a little confusing because isn't it two lines? Wouldn't the lines be in x, y space? Not exactly how it's going to work. So to give you a little idea of how it's going to work is we want t to equal 0 if the collision happens at P1, okay? And we want t to equal 1 if the collision happens at, oops, why am I doing s twice? At P2. And the same idea on s this time. So the s is going to range from there to there with Q1 and Q2. Alright, so that's kind of how we're going to set this problem up. So how do we do that? Well, what the equation looks like for P, if I remember correctly, is that basically what we're going to do now is we're going to take T and S, right? They are like a parameterization of these two lines, and we're going to represent those geometric lines, like the algebraic lines, I guess I should say, from P1 to P2 and Q1 to Q2 as variables of T, or in terms of the parameterization T and S. So for the line P, which is from P1 to P2, it's defined as some point x, y is in the line if it is equal to something of the form p1.x plus, and that's kind of a linear interpolation thing, p2.x minus p1.x times t, and p1.y plus p2.y minus p1.y. Now I'm writing this like it looks like code, using like dots and code syntax, but it's actually, I'm writing a algebraic expression here. So think of this as a system of equations, right, like I said. And then we also have the same thing for s. So the line of s looks like this, except it's going to be with q's and s's, right? So p's with q's, yes, 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 yes. And then t's with s's, yes, yes. Whoops, yes, yes, did too many. Guess I can just do these by hand and it'll be easier. Alright, so those are the equations. Now you're looking at this and you're probably thinking, well, that's 4 equations that we have. We have this equation, this equation, this equation, and this equation, right? If I expand these out a little bit more, it's like an equation here, and then an equation here, and then an equation here, right? So this is kind of what it looks like, we're actually saying. But we have all these variables. We have a variable for s and t, and also a variable for x and y. But the cool thing is we can eliminate the x and y's by saying, look, these two equations should just be set equal to each other. So it's really just a matter of this equals this, right? And a matter of this equals this. So that is the real system of equations that we're going to start with. But now, that's not a system of equations that I want to solve directly. I'm going to continue to do a little more algebra to clean things up. So we can get our constant term by subtracting the q1. So we would get this, q1.x. So there's our constant term. And then we're going to subtract the s over. And let's see, p2, it looks like p2.x minus p1.x is another term. So I'm going to subtract over the s part as well, and we would get p2.x minus p1.x times t minus s, right? And all of that equals 0. And then the same idea is going to happen on the second line, except on the second line the only big difference, p2 minus p1, oh, they're not the same. I see, I made a mistake already. So these are p2 minus p1, but these over here are q2 minus q1. So I can't just subtract the s over that easily. So that's okay. This is t, and this is minus. This should be plus, and this should be minus all of this, and that equals 0. That's how I remember this. I remember this being a little bit more difficult. And then these are the same, only it's y's instead of x's. So now we're getting a little closer to something nice, and you're probably thinking that's not very nice looking, it's even longer. What's nice about it is this is just a value now. This is just one value now. Actually, that with the negative, right? So we can compute this value. We really just have 6 values, and using a little linear algebra, this is just a matter of solving a system of equations. We could go ahead and make a linear algebra solver that's all full-featured and stuff, and maybe someday we'll evolve towards that, but that's going to be overkill for what we need to do here. So let's simplify the problem by actually storing some of these values in variables. So we have, we'll call it the first thing here, p1 minus q1.x. That is sort of the x constant and the y constant values, right? And then we also are going to have the tx scalar and the sx scalar, and then we're going to have the ty scalar, or this should be coefficient, that's a better word, coefficient. Might be spelling that wrong. Spelling is not what I do. Well, of the things that I do well, I wouldn't put spelling along on that list, that's for sure. So now I'm going to put some values in there. Let me check real quick how long I've been going, because normally I have this on a separate screen so I can glance, but not today. So there we go, that's going to be our x constant. We need a y constant. Okay, we need a tx coefficient. And a ty coefficient. And an sx coefficient, which uses the q's, and then an sy coefficient. Cool. So that means the changes we can make here are, it's like, I'll use an even more abbreviated variables now, constant, just makes it a little bit easier to think, y constant. And we said that the s's should actually be negatives, so it's like this. But the t, that's tx coefficient, is that smaller? It's actually not even smaller. What do you know? Still easier to think, I think. This will be the ty coefficient. This will be plus the sx coefficient. And this will be plus the sy coefficient. Alright, and then what we want to do is start solving for variables. So the way we do that is we can solve for t. That means we're going to, let's actually subtract these back over to the other side. So negative x constant, negative y constant. Okay. Now to solve for t, I just do that because that's the way I'm used to looking at it once I get it down to this form. So now to solve for t, we want to multiply this bottom part here by basically by the factor of I'll take this whole thing like this. So we're multiplying all of that by tx coefficient divided by ty coefficient, right? Because what that means is that that leftmost term will have the it'll have the same value as this, right? This will have a tx coefficient here and here. These will all get scaled by that amount. So what we need is this tx coefficient over ty coefficient to be stored real quick. This is going to be a super long form version of an algebraic solution, and we'll of course clean it up as we can once it's working. So basically this is the multiplier, and that's going to be this value here. And then we do ty coefficient. Well, we can ignore that one because that's just going to become a 0 later. It's going to become equal to tx coefficient, then when we do the subtraction it'll become 0. So we'll take these. This gets multiplied by the multiplier, and y constant, that gets multiplied by the multiplier. Now what I want to do is remove these negatives, because that's not fun to have that floating there. So let's make those negatives and pop these negatives up here. There we go. We multiplied both of those. The next trick is we can go ahead and make ty coefficient just 0, because that's where this is heading. I'll do that next though, because next what happens is we subtract from each term it's the term from above it. So this becomes this minus this, right? And since we said after multiplying this by this multiplier, it's going to be tx coefficient, we know that one is going to 0. That's the whole goal here. then what is the sy coefficient? What happens to that? Well, we take this and we subtract the sx coefficient. What about the y constant? We take it and we subtract the x constant. Now, another big problem with doing it this way is that this is because we're doing a lot more multiplication and division, we're going to have floating point problems sooner. But as we work on it, we're going to tighten it up, and then we're going to find a better mathematical solution that'll involve just less computations overall, hopefully. And in the meantime, I'm just getting the quick and dirty way working, right? How are we doing? Alright, let's wrap this one up. So we've subtracted all those out, and that means we're now at a point where we have a new form of this equation, right? So this will be, I'll put like a prime here to let us know that this is not the same thing as the original one. But what we have now is the sy coefficient after it's been multiplied and added to, and the y constant, and it's the primed version. I'll use a different notation to say that this is all, we can just put the primes like so. Prime of, put the primes after, because that's what you normally do in math. Alright, so sy coefficient prime times s equals y constant prime. Now, how do we solve for s? That's the easiest part. We just divide y constant prime by sy coefficient prime. Right, so now we have an answer for the first thing we needed an answer to. So let's wrap this up by just going boom here, boom, result. We'll start by, well, we'll just leave it like that. And the first thing we've finished is we've finished getting s, actually. S is now y constant divided by sy constant, or coefficient. So we have our solution for s. So the next thing to do, get the solution for t, which isn't too hard, but we're out of time. So thanks for tuning in. I hope you enjoyed it. Make sure to catch us next time. See you later.